Okay, so the next thing is the study of bifurcation theory. This plays a major role in everything we're talking about, and so let me jump right into it. So the point is that bifurcation theory is about changes in structure, in the structure of a dynamical system, in the structure of a dynamical system, which I'll abbreviate DS, when a parameter changes. All right, so we know lots of parameters in studying climate, so you can imagine that this kind of thing is ubiquitous. So we write this as in a sort of abstract way in terms of the vector field F depending not just on the state variable X but also on mu. So mu might be, X could be something like, I don't know, wind speed, something like that. Mu might be the parameter of temperature, or X may be temperature, mu may be CO2 content in the atmosphere, something like that. Or we saw the example in the Stommel model where there was a parameter eta 2, and as you changed that, the structure of the dynamics changed. Okay, so we're going to look in particular at what are called local bifurcations. All right, so that's going to be the focus, local bifurcations, and these are changes in the structure of the dynamical system that happens near a fixed point. Okay, so changes near a fixed point. So imagine that you have a fixed point of the dynamical system, and the question is, how might the dynamics change near that? So, I mean, for instance, we know about attracting fixed points and unstable fixed points, so you might imagine they go from attracting to unstable, something like that. Okay, and there are actually four different cases that we're going to, didn't mean to do that, the four different cases that we're going to study, and they are as follows. So cases, so one, the case where a fixed point disappears. Fixed point disappears. So as you vary the parameter, it just disappears. Okay. The second possibility is that fixed points collide. Fixed points collide. The third possibility is that new fixed points emerge. New fixed points emerge. And the fourth possibility is that a periodic orbit emerges out of a fixed point. Periodic orbit emerges out of a fixed point. Okay, and each of these goes by a certain name, and and they correspond to the different sort of key and critical things. I'm sorry, I'm trying to change. I keep pressing the wrong thing. Sorry, I'm just sort of learning how to do this. So these are the different cases here, and now what I want to do is I want to say what the names of each of these. So fixed point disappears is called a saddle node bifurcation. Fixed points collide is called a transcritical. Fixed points emerge is called a pitchfork, and periodic orbit emerges is called a Hopf bifurcation. So those are the names of the different bifurcations, and I'll explain why they're called what they are called. In some ways, the the distinction is not completely clean, in that the fixed points disappearing in a saddle node is really also a case where the fixed points collide, but they collide and cancel each other. The transcritical, I'm thinking of fixed points colliding and passing through each other. In fixed points emerge, you can also see it as fixed points colliding, because sort of in backward time they collide because they come out. The periodic orbits emerging, that really is very different. And I should give you a definition here of what a periodic orbit is, because that's a new concept that I haven't actually formally talked about yet. So a periodic orbit is an orbit, one of these solutions x of t, right, for which there exists a big T such that x of big T is equal to x at time 0. In other words, it comes back to itself after a certain time. Now that's a characteristic of a fixed point, but a periodic orbit is something that is not a fixed point, but does have this character of coming back to itself.